Last big property coming at you right now, at least for now, it's the quotient rule. So let's say that f of x is equal to the quotient of two other functions that are differentiable. So if f of x is u of x divided by v of x, as long as u of x and v of x are differentiable, then we have a nice, well, relatively nice way to find the derivative. And the derivation of this using first principles is much the same as the product rule. I'm not going to go through that in this video. But the derivative is going to be equal to low function times the derivative of the high function minus the high function times the derivative of the low function over the low function squared. The numerator can be thought of as saying low d high minus high d low. When I say d high, I'm talking about the derivative of the top function of the numerator. So here is our quotient rule. Let's go ahead and use it. So we would like to differentiate this. And you'll probably notice that, wait a minute, we did that in the last section, and we used the product rule. Yeah. Let's go ahead and use the quotient rule to differentiate the same thing. So the derivative is going to be low d high, so derivative of the top. And for the time being, I'm going to write it like that. I'm taking the derivative of x squared plus 1 with respect to x minus high d low, derivative with respect to x of x plus 1, divided by low squared. So now let's take the derivatives in the numerator. X plus 1 times 2x minus x squared plus 1 times 1 divided by x plus 1 squared. And I'm not even going to expand the denominator. The numerator, however, let's clean that up. 2x squared plus 2x minus x squared minus 1. Be very, very careful with this subtraction, because you got to remember you're subtracting all of that stuff that's coming after it. I'm a fan of never expanding the bottom. Leave it alone. Leave it as something squared. And on the top we combine like terms. X squared plus 2x minus 1 over x plus 1. Quantity squared. And that is the same thing that we ended up simplifying the product rule down to in the previous video that we saw. Example 2. Differentiate y equals x squared plus 1 over x squared minus 1, where x can't be positive or negative 1, with respect to x, and hence find the derivative at x equals 2. All right, so y prime. This is a quotient rule scenario. We could use the product rule. It's going to get messy because we'll have the negative exponents to chain rule and ick. I don't want to. I'm going to use the quotient rule. So low d high so there's my low d high plus minus high d low. All over low squared. And now we take the derivatives up on the numerator. 2x and 2x. And again, let's expand the numerator and combine like terms. The denominator, I will leave alone. Be careful here with the negative. 2x cubed plus 2x. And what we get for the derivative for y prime is negative 4x over x squared minus 1 quantity squared. And we wanted to find the derivative at x equals 2. So at x equals 2, y prime is equal to it's just a matter of substituting. So we get, I'm going to change this notation to dy dx. The change of y with respect to x is negative 8 over 9. And what that means is that at x equals 2, the slope of the tangent line is negative 8/9. Now, one thing to know is we can use our graphing calculator to help us with derivatives, ladies and gentlemen. It can't find it algebraically, but it can find a numeric value for the derivative, meaning it can tell you the slope of a tangent line at any specific position on this curve. So I've graphed our f of x in the previous example. I'm going to go into Menu, Analyze Graph, dy dx, and now it asks for the position. And I can either move my point on the curve, or since I know that I want the slope when x equals 2, I'm going to type 2 and push enter, and there we go. And you're saying, wait a minute, it was negative 8/9. What's up with that? Well, that is a decimal approximation to 3 significant digits. 0.8 repeating is 8/9. So graphically, we have verified the solution that we just got algebraically. And that, ladies and gentlemen, is the conclusion of our basic derivative rules. We are now equipped to find the derivatives of many, 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 many complicated functions without having to use our first principles over and over and over. Thank goodness.